In this video, we are finishing up section 11.3, geometric sequences and series. We already talked about generic geometric sequences and series, and you had the first homework already to do, 11.3.1. So we'll move on to some special cases of geometric series here and sequences. So the first one is an infinite geometric series, and it's simply the sum of the terms of the infinite geometric sequence. And so you can remember that just means dot dot dot. It means goes on forever. There is no end to the number of terms, so it goes on for infinity. So in this case, we're going to start with 64, then 32, and 16, and 8. And so you can probably see pretty easily in this case that r is 1/2. Okay, let's first figure out what some of the sums are. So the sum of the first term is just, well, that's easy, that's 64. The sum of the second term, that's 64 plus the second term as well, 32, and that gives us 96. And then the sum of the first three terms, that's 64 plus 32 plus 16, and that's 112. The fourth term, sum of the first four terms, that's 64 plus 32 plus 16 plus 8, and that is 120. And so you can see the sums, as they are getting bigger, you're adding more terms to them. The amount that we're adding each time is less, right? So the last one we added here was 16, then 8. So as you increase the number of terms in the sum, the total is decreasing. The total is increasing, but at a decreasing rate. All right, so rather than continue that, let's just look at what S sub 7 is. And instead of using that approach, let's just go back to our formula. That's going to be 64, the original term, minus 1 times 1 minus r. R is 1/2. Raised to the 7th power, because that's the number of terms that we're looking at, and then 1 minus r, so 1 minus 1/2. All right, and that ends up giving us 127. So we added 3 more terms, but we really only added 7 in the value of the sum. So you can see it really is decreasing. The sum is increasing, but at a decreasing rate. So again, let's do that same thing for the sum of the first 10 terms. So we'll do 64, 1 minus 1/2 raised to the 10th power this time, 1 over 1 minus 1/2. That ends up being 127.875. So you can see that it's decreasing very quickly, right? I mean, the amount that we're adding. So we added 3 more terms, and we only got another 0.875 added to our sum. So if we sort of look at this, step back for a second and say, okay, so it looks like it's kind of slowing down. What do you think the total sum is going to be if we go out to infinity? Well, intuitively, it doesn't feel like it's going to, but it will approach an actual value. So if we look, let's look if we went out to infinity terms, infinitely many terms. So we have the first term, 1 minus r to the 1/2. So if we plug those values in, we have 1/2 raised to the infinity. All right, so what do you think this value is going to be? Now, we don't really have a way of taking 1/2 raised to the infinity power, because infinity isn't a number, so we just can't take 1/2 and raise it to infinity. We just don't have the mathematics to actually do that. In your next math class, we will talk about something called a limit. So we'll say the limit as n approaches infinity of 1/2 raised to the n power. So what will this equal as n approaches infinity? So we can't put an actual value in that, but this thing's going to get closer and closer to 0. Okay? It kind of makes sense if you try a couple of these. I mean, take 1/2 and raise it to the 1,000th power, right? It gets really, really small really quick. And so if that indeed goes to 0, then you can kind of see this formula is really just 64 1 minus 0 over 1 minus 1/2. And so that ends up being just 64 divided by 1/2, or 128. So we might have guessed that we were going to approach 128. We were getting closer and closer to it here. If you had done maybe S sub 20, you'd see it's even closer yet. But 120 is the value that this series, if we add up every single number, it kind of feels weird the first time you think about it, because you say, well, you're still adding something, so how can it just be a particular value? You're going to start adding such small numbers as you go further out. Even the 20th term is going to be so small that it will be approaching 128. So, so as n approaches infinity, the sum of those n terms approaches 128. So we can think of it as the limit as n approaches S of n is 128. Okay, so when will this happen? In other words, under what conditions will this approach 0? So it approaches 0 in this case. Will it do that for every r? For what r's will this happen? And so that kind of talks about it in this next formula here. So that's going to happen when r is less than 1, because when r is, say, 2, like we saw in some of the previous examples, when r was 2, the number just keeps getting bigger and bigger. So this doesn't approach 0 if r is 2, because 2 squared, 2 to the third, 2 to the fourth, it keeps getting bigger and bigger. Whereas 1/2 raised to some huge number is going to get closer and closer to 0. So, so in general, we have two conditions, right? We have the magnitude or absolute value of r less than 1, then it's going to converge. And the infinite series, I guess what we surely should think about is this: instead of S of n, this should be S of infinity. So S of infinity, if r is, the magnitude of r is less than 1, then this thing will converge to this value. Now, if the magnitude of r is greater than 1, then it's not going to converge, and it does what we call converge. And so it does not follow this formula. We cannot use this formula. It only works when the magnitude is less than 1. All right, so try the next two problems and pause the video. Try figuring out these next two, and then when you unpause your video, we'll replay. We'll show you what the answers are. All right, so this first one, what we first have to kind of think about is pull out some numbers out of this. So what is the number of terms? Well, the number of terms, well, that's infinity, right? So we don't have a set number because it's going from 1 to infinity. So there's infinitely many terms. All right, what is the first term, a sub 1? Well, that's this first thing here. If I put a 1 in, that makes this a 0, so that part goes away, and so we're just left with this as our first term, a sub 1. So a sub 1 equals -2/5. And then our r, well, that's how much we're going to multiply every time, and so that's how much it's going to increase by, get multiplied by every time. So r in this case is -1/3. All right, so that's everything we need. The magnitude of r is indeed less than 1. In this case, it's negative. That's fine. Still works the same way. So now let's use this formula. So s sub infinity is equal to the initial term, which is -2/5, divided by 1 minus -1/3. And if you simplify all that, you end up with -3/10. So this thing will converge to -3/10 if we go out to infinitely many terms. All right, next one. All right, so again, it's going to be infinitely many terms. What is a sub 1? Well, I used the first value of the summation index, and that's 1. When I plug it in there, clearly this is going to be 0.9. The r is also 0.9. All right, so my sum of infinite series, infinite geometric series, is going to be the initial value, 0.9, divided by 1 minus 0.9, or 9. Okay, so now let's look at the last page of our notes. And so these are going to be dealing with some special situations of infinite series. And so this is called an annuity. So an annuity is a financial mechanism by which you deposit a set amount of money on a regular basis or withdraw. So if my retirement savings might, upon my retirement, be turned into an annuity, which is guaranteed to give me so much money on a regular basis every month, and for 10 years or whatever. So let's look at an example. So we plan to save for vacation, and at the end of every year, so we save every year, and at the end of every year, for 4 years, I deposit $1,000 into a savings account that pays 2% interest, compounded annually. Remember, this is the formula for compounding interest on an annual basis. All right, and remember that in the real world, we could have t be something other than 1, other than a natural number, but in this case, we're going to talk about whole years. So, okay, so how much money is in the account at the end of 1 year? So at the end of the first year, I deposit $1,000. So there is exactly $1,000 at the end of the 1 year. I just put that money into the account. All right, and so at the end of the second year, well, at the end of the second year, I'm going to add another $1,000, but I'm going to have this $1,000 from last year, and it will have gained some interest. So it's 1,000 times 1 plus 0.02. Well, let's just add that together, I guess, and we'll do it as 1.02. And just to be clear, I'm raising that to the first power because that was only in there for 1 year. All right, at the end of the third year, I deposit another $1,000, brand new, into the account. And then this $1,000 has now been in there for 1 year, and so it has interest. And then this amount is in there for another year, so it has $1,000 times 1.02 raised to the second power because that amount has been in there for 2 years. All right, now fourth year, same kind of thing, 1,000 plus 1,000. This amount has now been in there for 1 year. Everything kind of shifts over. This amount now is in there for 2 years. And this amount has now been in there for 3 years. Okay, so we could pick up a calculator and calculate what all that is. But that gets a little bit cumbersome to sort of do that past 4 years. If I did that for 20 years, that would just be too cumbersome. So really what we want to do is think about the formulas that we were just using. So the initial amount at the end of the first year, $1,000. And then the R, in this case, the interest rate is 2%, but our R, based on the formulas that we're doing, the R is this value in here. So the R is 1.02. And so if we plug all that in for 4 years, we have $1,000 is the initial amount. So we look at looking at this series, right? So we have one value, this is the second term, the third term, and the fourth term, adding those up rather than taking a calculator and doing that. We can simply just do 1,000, 1 minus the R of 1.02 raised to the fourth power, and then we do all over 1 minus 1.02. And we plug all that into our calculator, we get $4,121.61 to the nearest penny. Okay. All right. So in general, we have this formula, but the R, we have this formula here, but the R can be replaced with something that deals with more of the interest rate, and so then we replaced it with 1 plus I being the interest rate per year. And we do that on the bottom too. Instead of 1 minus R, it's 1 minus the quantity of 1 plus I. And so on the bottom, the ones will cancel, right? So it's 1 minus I, and so we have negative I on the bottom. That negative can be moved up, and we go ahead and distribute it inside this part. We don't leave it out with the a sub 1, and then we can flip around these things. And so this generates that formula for an annuity, or a future value of an annuity. So S is the final value at some future date. R is the amount put in at a regular interval. I is the interest rate per period and the number of periods. Now we're going to limit ourselves to, for the most part, the periods will be 1 year periods. All right, so for example, 9. So to save money for a new car, Clayton deposits $3,500. So he saves money, and at the end of every year, he has $3,500 saved up in his mattress, and he goes to the bank and he puts it into his savings account. So at the end of each year, for 6 years, he puts the $3,500 into an account bearing 3% interest, compounded annually. Find the future value of his annuity. So we could think of, like, what would this look like if we kind of wrote it out like we did up here. So at the end of 6 years, he would have $3,500. That would be the last amount that he had put in. And then the very first amount that he put in at the end of the first year would be 3,500 times the R, which is 1.03. And it was the end of the first year. So at the end of the 6th year, he's had 5 years to gain interest on that amount. So we can think of this as our first term and our last term in our series. Even though this was the first amount put in, this was really the last amount put in. We want to think of adding this up as a series. So this is a sub 1. This whole thing is a sub 6. All right, so let's find the sum. So although we didn't really need to figure out this thing here, I was just trying to write this out similar to how we did it up there. We just want to use this formula. So the amount he regularly puts in, $3,500. And then we just simply use this formula. 1 plus, well, I'll go ahead and put it as 0.03 for now. I mean, we could have just written that as 1.03. And then that whole thing is raised to the 6th power. And then we subtract 1 from that. We divide it by the I, not by the R in this case, but by the I. And when we put all that into our calculator, we get something like $22,639.43. Okay. All right, so your homework is listed there at the bottom of the page.